Okay, so great, welcome. And let me do this. I will quickly, in sort of telegraphic style, will tell you about a couple of problems I'm doing for this collaboration, and then I will tell you the story. There will be one project with Nikolai Prokofiev, about which I will hopefully tell you a little bit more detail. So you saw this many times. This is our goal. And one corner of this is superconductivity and strong coupling. Nick and Jonathan talked about this, but let me say a few more words because I think it's more theoretical but still important part of our developments. Then valley and spin degrees of freedom. And surprisingly, I will say a few words about this flat bands, but flat bands will come out in a slightly different environment. So let me start with superconductivity and strong coupling. This is project going with you, who is wonderful new postdoc in Minnesota. And basically, let me tell you what we want to do. It's study of fundamentally, and I use the word fundamentally here, non-BCS superconductivity in a situation when the system is close to a quantum critical point, which can be pneumatic, magnetic, and it's the same stuff that people studied in Yukawa SYK, so the problems are almost identical. And the story here is that players are fermions. They're collective modes, so it's not phonon-mediated pairing in this regard. It's pairing by collective excitations of fermions. And again, these collective excitations can be of magnetic origin, of charged pneumatic origin. There are a number of cases. And simplest thing you can imagine, you have a coupling between between fermions and collective modes in a proper pairing channel. And at the end of the day, what we're doing, we're solving Eliashberg equations, or Eliashberg type equations, because it's, strictly speaking, not Eliashberg problem. But the same set of equation and frequency domain. One for pairing vortex. People used to think more about superconducting gaps. They are just related via self-energy. And the second one is self-energy. And this problem has been studied in various aspects. And you heard the talks yesterday and the day before yesterday that named these equations. The input here is the form of the propagator, not input. Well, yeah, to a certain extent. It's input because you calculate it separately. And in a number of problems, and most all problems which are far away from the critical point, you can have a very complex form of this propagator. But at the end of the day, one is important. That in the limit when frequency goes to 0, this guy goes to a constant. And after that, the problem becomes pairing in a Fermi liquid due to some particular frequency-dependent interaction. It can be very complicated. It can be difficult to solve. But this problem is not qualitatively different from a Fermi liquid pairing. I mean, the game is to find accurately the form of the gap, TC, etc. But at the critical point, there is one qualitative difference. This effective interaction, because boson is gapless, diverges as some power of frequency. Power, which I label here as gamma, depends on the type of model. In SYK models, there is a way to gradually control this power. But in any case, this is qualitatively new problem. And it's just to tell you the list of people, a number of them are sitting in this room. They're studied various aspects of the problem. Again, SYK is one aspect here, pairing near a critical point is the other, but at the end of the day, equations are the same. And the only thing I want to say here is that you take generic gamma, you calculate self-energy in the normal state, and the word non-Fermi liquid means in practice nothing but the fact that self-energy scales as frequency to some power smaller than 1, so bare omega is never a competitor to self-energy. Okay, so what we are interested in, this problem has been studied before, and I'm not going back in time to discuss the aspects of all aspects of the problem. Basic physics is competition. Self-energy wants non-Fermi liquid, pairing interactions want superconductivity if self-energy is not interfere, and they basically try to tick-a-tack play a game with each other. Depending on who wins, the system either remains non-Fermi liquid or becomes superconductor. And long story short, at the end of the day, superconductivity always wins. So out of this loser-winner, superconductivity is a winner. There is TC that is present for all values of gamma. Everything is fine. And the interest for this collaboration, at least part of the interest is for this collaboration, is that even if coupling is weak, because bosons are gapless, you never get exponentially small dependence on the coupling constant. What you get is linear dependence on the coupling. G is the coupling here, just overall factor in susceptibility, and some function of this parameter in the theory, which one can calculate, but it's never exponent. And I guess Terra emphasized this for flat bands. Here it comes out as a result of gapless collective modes. So where is the interest? The interest is here. You look at solution of Eliashberg equation. And you used to say, well, we're below TC. How many solutions of Eliashberg equation do we have? Normally we say 1, and this is the solution. At critical point solution of the linearized gap equation, we go below TC, there is a solution of nonlinear gap equation. We're all used to this. Here the story is different. There is infinite number of solutions of Eliashberg equation for any temperature below the largest TC, and these solutions are topologically different. On the surface, topologically in the simple sense of the word, namely that solutions, just label here different solutions. If you have a lot of computer power, you can get this pretty strongly. But number of solutions is basically number of how many times the gap changes sign as a function of Matsubara frequency. And this is just, actually, that's a real number. So we can find that we did, in fact, found all the solutions. And why it's interesting? It's unusual. It's definitely not BCS. BCS will tell you only this and nothing else. Then why topology? Because every time the gap changes sign on Matsubara frequency, if you convert this function on the real axis where you actually do measurement, you find that the function is complex. This is now function on the real frequency. Any function of frequency, which is real on Matsubara axis, is complex function of frequency on the real axis. It has amplitude, it has a phase. And if you see how phase winds between plus and minus infinity or frequency, or because it's all even, half of this will be between infinity and 0, you find that there are 2 pi times n number of phase slips. And this is topology. This is something that in principle can be measured in experiments. And in fact, people in Sergei Borisenko group in Dresden at one point tried to measure phase of the gap as a function of frequency along real axis. But here is one caveat, that you do calculations, and you find that the largest TC, largest gap, largest condensation energy is for boring solution which doesn't have any of this. And so it looks like so many efforts are all in vain. You try to do it, you get something interesting, something non-trivial, but at the end of the day, condensation energy is the largest for most trivial solution. So again, without going into details, I say that will be telegraphic style at the beginning. What we are doing, we're searching for conditions, how one can kill the first solution, and go and find out that the second one, maybe the third one, will eventually have the largest condensation energy. And by word the kill, I mean some physical process that will kill this solution and make propellers this one. We're not only looking at this one, propellers this one, which is really topologically distant from the first one. And we did find conditions when it happened. So we'll report about this later. Yeah?
Why not add repulsion?
Well, this is, I guess, I said we find conditions. So I will tell you exactly what conditions we are, but it's more than just adding repulsion. If you just add repulsion, you kill all of them. It turns out that you go this way. You need to be a little bit more intelligent here. Sorry, not you, of course, it's for us. Sorry. Yeah. Yeah, ask me later. The other stuff, again, in a sort of telegraphic style before I move to the story, is the work we do with another postdoc in FTPI, now FTPI postdoc, Vladimir Calvera. We have actually a stream of both people who were graduated in Stanford that are moving to Minnesota. I think it's a good sign. So this picture you saw many times already. You saw it on Wednesday, you saw it on Thursday. This is superconductivity in a quarter metal phase, which is basically both valley and spin polarized. And the question is how to explain this superconductivity. And there were previous talks by a number of people, I'm sure that the list here is not complete, who were talking about this. And Stefan will probably be talking also about superconductivity in a half metal state, which seems to be ferromagnetically ordered. And this superconductivity, at least one of them, near the border of ferromagnetism. So in previous life means before this week, I did some calculations about what mediates superconductivity if not phonons. And the story here is that if you are in the fully half metal state or fully quarter metal state, longitudinal fluctuations of your order parameter, say spin order parameter, doesn't matter. You have maximum magnetization. You cannot make it larger. So the only degree of freedom that exists are magnets. Magnets are Goldstone modes. And so I went back to the story that people studied with antiferromagnets at the beginning or at the middle of high TC era. Can collective excitations that obey Goldstone theorem and Adler principle still mediate superconductivity? And the answer was yes. You can get attractive interaction in the P-wave channel, which is good. And that was the case mostly for what I want to say quarter metal, when they have one valley and one spin. But this was basically baby calculations, in the sense that I just used parabolic dispersion, one band, and ask a question, do we have attraction coming from magnets? What we want to do now is to follow Andrey's work on this trash can, and much more than just the name of trash can, and include things that he discussed, form factors. This is what we want to add combined with magnets and see what we get when we do both. Then, of course, we want to redo calculations for flatter dispersion. We don't want to use exactly trash can, but something like dispersion k to fifth, but it doesn't matter probably much. And this is what we already did. This interesting effect of fermionic self-energy in this problem. Well, sir, we're serious. We want to put self-energy every time when we see its possibility. There's an interesting effect on TC. And very last, just to mention, with Aries, we have another project. Basically, it's a simple question. Suppose the system goes into half metal state and then into quarter metal. So it goes from half metal to quarter metal. We normally used to say, well, there are interactions that give rise to one instability to the other instability. One comes first, the second comes not distant second, and so one follows the other. But there's a feedback effect. Once the system undergoes first instability and reconstructs excitations, it reconstructs polarization bubble that is responsible for susceptibility in the other channel. And what we are trying to see is what is the feedback from one order on the appearance of the other, and whether the appearance of one order selects particular appearance of the other. For example, spin polarization will select either valley polarization or IVC, for whom the first order will be more favorable. So this is basically what we're trying to do with Aries. And with this, switch gears, now the story. The story is the work with the person sitting on the second row over there, Nikolai Prokofiev, the member of our collaboration, and Ilya Yesterlitz, who is currently in my office in UW Medicine. It's actually literally in my office. There's motivation. And motivation is this one. We heard talks about whether Migdal-Eliashberg theory can be extended to strong coupling. Original idea, you remember, from the giants in the field, that there are two parameters. One is coupling, another what's called Eliashberg parameter, which is coupling times the ratio of Debye frequency over Fermi energy. And when the first one is already large, the second still can be small. And you can then do calculations in a self-consistent one-loop fashion. Basically, it was a question, can we justify self-consistent one loop? And what Aries said is, I completely agree, there is another way to do it. You extend theories to large n, do a proper large n. You need to do proper way of large n. But then again, self-consistent one loop is justified, vertex corrections are small, and you can extend theory to strong coupling, where, of course, superconductivity is enhanced, et cetera, et cetera. But again, this is what I mean. In a conventional case, strong coupling for electron-phonon interaction means something that, I guess Minuel said explicitly, that TC is given not by Macmillan formula, by Allen-Dynes formula. Formula is specific, as written here, is specific for strong coupling. But nevertheless, this is what the idea is. Can we ever get this? And Steve did a lot of work in this regard with other people. Andy did a lot of work, and I put names of people who were talking about this, plus, of course, completely incomplete list of names who were working in this field. And from the generic point of view, if I look at Migdal-Eliashberg theory as a theory, what can go wrong? Well, it's my personal. Phonon can soften at some momentum. This has been seen. This has been seen in a number of numerical studies. I will show you one later. This means charge density wave instability. It can be that the phonon softens at Q equal to 0. Then we believe, I don't think that anyone showed this completely explicitly in terms of go beyond instability and see how order develops, but we believe that this leads to phase separation. Vertex corrections may become large at some point, and this is another thing. Even before phonon softens, it can be that the theory breaks because corrections in the theories get stronger. And it is discussed, this is what Boris Alshoy and Min Yuzabashyan proposed recently. There may be some internal dynamical instability for which there's some indication, but it's not entirely clear what it leads to. Yeah. That, well, what I mean by phase separation is that density is larger in some region of the system and smaller in the other region of the system. Electron density, of course, yeah.
With no periodicity.
With multiple periodicity, if you like. It's just, I view always phase separation as a combination of charge density wave, the infinite set of charge density wave, which produces it. But let, yeah, yeah.
So I have some sort of, okay.
Yeah. Okay. Okay. So here is what we will argue. We'll argue several things, and then I will show you how we argue this. We argue that there is another reason, which people already know, instability towards formation of bound states between electrons and phonons, which are called polarons. And if you allow polarons to interact, then they form bipolarons. And this is another type of instability. So basically, we argue that this instability has nothing to do with Migdal-Eliashberg theory. And it happens, we know the region of parameters, basically small density, in which it definitely happens when Eliashberg theory or Migdal-Eliashberg theory taking on a face value is completely stable. All parameters are such that you never think about instability of the theory. I will show you the results in 2D, but in 3D, it turns out that you have just parameter range, real parameter range, where this happens. And at higher density, yes, there is some region when polars don't form before spin density wave is formed. Then there is a region of strong coupling theory, but it's not Migdal-Eliashberg theory. It's a quantum critical theory near a charge density wave transition, and then TC is not given by Allen-Dynes formula. Allen-Dynes formula assumes that phonon frequency goes down, but phonons remains momentum independent. This is not what happens. You have fluctuation, critical fluctuations only near a particular Q. And I guess it's an important distinction. But one of the main messages of what I will be talking about is that Migdal-Eliashberg theory is a wonderful theory, but it's low energy theory. We used to do low energy theories saying that linearize near the Fermi surface and everything comes from near the Fermi surface. And by the way, reminder, expansion parameter, it's called lambda in the Migdal-Eliashberg theory, is proportional to density of states at the Fermi level. So it knows about fermions at the Fermi level. We argue that polaron instability comes from high energy fermions with energy of order of bandwidths. So it's a totally different type of instabilities unrelated to Migdal-Eliashberg. Okay, so here's what I do. Now the calculation. Three. I will put 3 scales right now. Okay, go ahead. Yeah.
Okay, but on the previous slide, there was just 1.
Can you use your seat mic, please?
Wow.
Yes.
Wow.
Yes. So, but on the previous slide, there was only 1 energy scale, right? The bandwidth.
Oh, there is bandwidth, but bandwidth needs to be compared with something, right?
Yeah,
So
okay.
basic message is that Migdal-Eliashberg theory is a theory at which you essentially probe behavior of a system at frequencies comparable to the Debye frequency.
Regardless the Fermi energy?
Even if Fermi energy is large. Again.
No, large is I understand, but if it's small.
Oh, no, I'm not talking about that case.
Okay,
Look,
so
this is why I'm saying, let me just
okay,
put
fine, yeah, thanks.
parameters. No, good point, but
All right,
I'm
no,
not
okay,
talking
yeah.
about this. So here's what I do. I will do something that is completely textbook example, just to show you what's the point we're trying to make. Let's take fermions. Just for sake of the argument, nothing more, I will take tight binding dispersion. Take any dispersion you prefer, including parabolic. Then the results will just mildly depend on what you put in. Einstein phonons, the form of propagator, what I put in numerator, of course, is related to how I define coupling. And coupling, Yukawa coupling. So now answers the point. There are actually three-dimensionless parameters. One is the ratio, one is the coupling constant, which notice I defined not as an Eliashberg theory. I defined it with bandwidth in denominator rather than density of states at the Fermi level. Second one is the ratio of the coupling over Debye frequency. And the third one is this Eliashberg parameter, the ratio of Debye frequency over Fermi energy. And it's assumed to be much smaller than 1 all the time, no matter what. So even if I take a limit when density goes to 0, I say take it as a sort of double limit, keeping this parameter always small. So I never go into a situation that Leonie was talking about or mentioning about when Debye frequency and Fermi energy are comparable. The story is not about this. Moreover, so this parameter will basically doesn't appear. I will take this guy and will assume that it's large and fixed. So meaning that interaction will always be larger than Debye frequency, where again, Debye frequency is the smallest parameter in the problem. Again, this is the best case for Migdal-Eliashberg. And I will vary this parameter, just I need to vary it somehow. I will vary it by varying bandwidths. So large bandwidths means that we're at weak coupling, small bandwidths meaning that we're at strong coupling. I just need to vary, and I can vary it in different ways. So this is the way how I will vary parameter. Very good. So what we're talking about? One thing very quickly. It's just a matter of presentations. In numerical study, we did both numerical and analytical studies. In numerical studies, we consider fermions with spin 1/2, so these are real spinful fermions, and then bound states are actually bipolarons. In analytical study, just not to deal with bipolarons, we considered easily handle problem, which is fermions are spinless, and then it's only polarons, but no bipolarons. And in the formulas and the results I will show you, I will just focus on this part. We have results for bipolarons, so if somebody is interested, we can show a bunch of results for bipolarons as well. There is no qualitative difference between these two cases. Okay, now with this. Borrowing the style from Steve, I present empty phase diagram, and then I try to put some stuff in it. So this is phase diagram that I'm interested in. Density along this line, coupling along vertical line, and everything is symmetric with respect to 1/2. So it's situation that n larger than 1/2 is mirror image of what you have for n smaller than 1/2. So I stop here at 1/2. And so let's start with what we know. Yeah, that's what I said. Let's do weak coupling first. Weak coupling is done by virtually everyone in this room. Conventional Migdal-Eliashberg theory, perturbation theory in the coupling, weak coupling if lambda is small, moderate coupling when lambda is of order of 1, and density of states is continuum. It doesn't have to be this free fermion density of states. It doesn't have to be like this. There are, of course, self-energy correction, but it's continuum. It's continuum, whether it has a logarithmical divergence at omega equal to 0, it's all detail. Basically, one continuum with the width W. That's all I want to say here. What can we obtain within this theory? Obviously, we can obtain when this theory becomes unstable towards density wave formation. And yes, there is a line which one can calculate by explicitly calculating polarization bubble. Again, whether to include self-energy into polarization bubble or not, a second order question. There is some line. And line goes down as density goes up, in fact, vanishes at 1/2. But here is the important part. Remember this number, pi over 4. Just a number. It comes out for this tight binding dispersion. For other dispersion, it's a different number. But just remember this number. This is basically when phonon softens. We know momentum over which it softens. This is basically transformation from momentum finite q to stripe momentum pi q and q pi, but it doesn't matter. All these are details. I showed just one picture from Ilya, Steve, and Doug paper. You go like this. Everything I will be talking about is 0 temperature, by the way. Just again, I have only, 15 minutes left. So you go along this line. Yes, there is some superconductivity here, but the system becomes unstable towards this commensurate charge density wave order, and its story pretty much like this. Very good. Let's now switch gears. Let's ask ourselves, what happens in the opposite limit? And I want to go to extreme. Opposite limit coupling is equal to infinity. What that means? Bandwidth is 0. So this is precisely why I put lambda 1 over lambda. I want to be at the point 1 when coupling is infinite. And ask the question, what do we know about that limit? We know exact solution of Hallstein model in this limit because it's single-site problem. An exact solution tells you that density of states is very different. There is no continuum. And remember, continuum has one peak. Now, density of states is like something that we used to say with the word pseudo-gap. The density of state has 2 peaks, but it's not simply peaks. Density of states is a bunch of delta functions. These delta functions are separated in frequencies. It's basically integer number times omega naught, and the peaks are when this integer number is beta. And remember, beta is number much larger than 1. So don't look how many peaks are here. There's 10,000 peaks between, yeah. Yeah, yeah. Well, within this model, it really, when bandwidth is equal to 0, that's all what happens.
Okay.
Yeah.
Right. So when bandwidth is equal to 0, it is an atomic.
Yeah.
System.
Yeah.
Okay.
Yeah.
Okay. Good.
Yeah.
Thank you.
Very good. Yeah, and there are analytical formulas how this density of states looks like, again, from exact solution. And I asked a pedestrian question. And pedestrian question is this. How is that transformation from one continuum density of states with one peak transforms, how this density of states transforms into density of states with 2 peaks and with a bunch of delta functions? How to do it? And at which coupling this happens? How it's related to the coupling at which Migdal-Eliashberg theory becomes internally unstable because of charge density wave order. So basically, this is what we want to do. Again, it doesn't have to be exactly like this. It should be single density of states, how it transforms into that one. And now, 2 minutes about mathematics. Here, we know what to do. We know that density of states is integral, k integral of the retarded Green function. We start with free fermions. We put in self-energy. It depends on how much time we have or interest, how many diagrams we sum up here. And again, Migdal-Eliashberg theory will tell you only sum up self-consistent one-loop diagrams, don't sum vertex corrections. We know how to act. And we know that, it's important, we know that when we do this, we do not destroy single continuum feature of the density of states. Andrey Marie did a lot of work with respect to spin fluctuations in this card. They were the first to introduce really very accurately self-consistent one loop. And yes, you broaden, you change the form, but you still have single density of states. What our goal is? Well, can we do the same in the opposite limit? Do something crazy. You start with free fermions, but no dispersion. And then, this is basically what you want to start. Mu has to be determined such that the density is just whatever n you take. And then ask questions, can we do diagrammatics? And why I want to do it? Not because I want to explain this with diagrammatics, because then I can add bandwidths. And then I have the same description here and here in terms of the same fermions. So then I will try to go continuously from one element to the other. So the first question very quickly is, can we do perturbation, not the diagrammatic theory here and obtain this result? And the answer is yes, I already put it here. And it's a wonderful story, which If you give me 2 hours, I will tell you a story about zero density and about finite density. Since I have probably 10 minutes, no more, then I will only tell you about zero density, because the description is a little bit different in 2 cases. So basic message is, don't even think about self-consistent one loop. Sum up all diagrams, everything. Beauty here is that when you have no dispersion, all bubble graphs give you 0 because poles are obviously in the same half plane without dispersion. But so it's basically like one line, and you put everything. You put self-energy, vertex corrections, diagrams to infinite order. And it turns out that this can be summed up in a simple version of the problem. It's called A canal, but this is extension because you take the bifrequency finite, and it should work. Yes. This is how this crazy diagrammatic theory works. I already assume that, well, I already know what chemical potential will be in order to satisfy conditions as the total density vanishes. So I just put it here right away, although it needs to be calculated self-consistently. And I just want to show you that when you do this perturbative calculations, you get more and more poles. You start with one pole, you start getting poles, which is not bad. But if you look where you get the poles, you get the poles here. You start with this one, or this one that I almost erased, and then you start going this way. You don't get anything here, nothing. You don't get any bound state. You get only anti-bound state, if you like. Very good. Moreover, if you are here, and you want to see what happens at 0 frequency, or it's very small frequency, it doesn't matter. Everyone will look at this expansion. Remember, beta is large parameter. You say, well, it's great expansion. 1 over beta square, 1 over beta cube, etc. Beta is large. Why not to say that, great, then there will be nothing here. Just no pole, meaning. It turns out that all is wrong. That, in fact, this is a special case, and the whole story about polarons will be reflection of this special case. Call it special or not that special, that perturbation theories are not convergent. And they're, in fact, not convergent for any frequency. The story is that, yes, you sum small powers and small parameters. You ask, what is this overall combinatoric factor in the series? And it turns out that this is essentially n to power of n. 2n plus 1 factorial, let's say, or large n is n to power of n. And then combinatoric factor will overshoot smallness of your expansion parameter, no matter how small parameter is. And yes, I will not give you full details of how to get the result. We did calculations, blah, blah, blah. And just to emphasize or impress, the result is expressed in terms of cumulative hypergeometrical function. It should be hypergeometrical function. But in fact, it's a combination of gamma function and extended gamma function, or generalized gamma function. And poles of gamma function is your delta functions in the density of states. And so you reproduce completely. Remember, its density goes to 0. There's nothing here. So you reproduce completely the exact result for the Hallstein model, which means that it's not just to show that we can do it. It's to learn a lesson. And the lesson here is very simple. Results come from higher orders in diagrammatics. If you want to stop with any order in diagrammatics, you just don't get all this. And in fact, this peak at 0 frequency, if you basically see this density goes to 0. So thermodynamics is determined by this one, in fact. So basically, again, message here is that you want to stop with nth order of perturbation theory, you will not get this result. You need to resum, doing Borel summation, and this all wonderful mathematics. But at the end of the day, you do it, and lesson is this one. Very good. Now I have this. Great. Let's introduce finite bandwidths, since I just can extend the calculations to a finite bandwidth. And here is what's going on. It's very similar to the result that Murty and Steve obtained some time ago. That if you look at low frequencies, remember, all peaks we had, these were delta functional peaks. If you look at low frequencies, you basically keep the peaks as they are. Yes, bandwidth appears. And you can say, well, generally, bandwidth should be much larger than the bifrequency when something becomes interesting. Yes, but it turns out that z factor of these excitations are exponentially large. And as a result, effective bandwidth is exponentially small. As long as this parameter is large, we can keep W times small exponent smaller than anything we want, including the bifrequency. So this has separate peaks. Up to what frequency? Well, it's a gradual process, of course. But if you go to large frequencies where this delta function has the largest residue, that residue was of order of 1. So you put bandwidths, and of course, when bandwidth is larger than omega naught, you stop seeing individual peaks. So what you see at large frequencies is essentially continuum. Continuum whose width quickly becomes of order of W. Basically, the distance between this point and this point is W. And then we have a wonderful story. The story is that total density of states at finite bandwidths consists of peaks. This is, of course, cartoon. Consists of peak coming from low frequencies, then, of course, gray area, and then continuum that's sitting originally at higher frequency. This is beta omega naught. This is 1, 2, 3 omega naught. Consider beta 200. And so you see the difference between the two. And then you start increasing bandwidths. And when you're increasing bandwidths, what happens is that the big elephant comes towards small frequencies and eats polaron one by one. This, again, cartoon. This is just eating one polaron, eating the other. Of course, it's not entirely like this. I just want to show you what's going on. Finally, it reaches 0 frequency, eats the other polaron, and this is where polaron state ends. And we know precisely when this happens. We have some benchmark also to check this precisely. And so this means that the last bound state here disappears basically when half of the bandwidth is the distance between beta omega naught and 0. This is actually exact result. For n equal to 0, this works. So we have critical value of 1/2. And this 1/2 is when polaron transforms into Fermi liquid. And if you want to read it from right to left, then you read it different way. You start with Fermi liquid. And then you ask a question, when the first bound state appears? And it's a funny story. Bound state appears at 0 frequency. You may say, well, this is low energy phenomena. But you may ask from where this bound state comes from. And then it turns out that it comes from higher order diagrammatics. In any order of diagrammatics, you start moving your frequency to larger and larger values. As long as you're in the bandwidth, it's just conventional perturbation theory. Integration over bandwidth eliminates all interesting features. But at some order of perturbation, you go here. You exceed bandwidth. You go into open field. And this is where perturbation theories don't converge. So this is where bound state comes from. So it's really a story that if you focus on this region, nothing happens. You need to find out what happens with your perturbation theory here, meaning that higher level, higher order of perturbation theory. And this is exactly the lessons that we had from calculations at 0 bandwidths. Practic, remember this number, pi over 4. There's another number, 1/2, smaller. So basically, you go like this. Nothing happens with your Migdal-Eliashberg theory. It's perfectly OK up to this point. But other state has lower energy at smaller value of the coupling. So you can reconstruct your excitations. You start forming bound state. So in simple language, this is where bound states form. And again, I keep repeating, to get this bound state come from high energy fermions. You will not get them in the theory that only knows about low energies. OK, now very quickly about the very rest. What happens when density is non-zero? Then calculations are in some sense order of magnitude more involved. So let me not go into this. I'm looking at how much time is left. So let me tell you what the result is. And the result is sort of expected. Instead of having, remember, there was a bunch of delta functions here. There was a bunch of delta functions here at finite n. Each set separates into delta functions at small frequencies and continuum at larger frequencies. And then predictably, these two guys come closer to each other, eat polarons one by one in the process, and finally just collapse. And when they collapse, this is Fermi liquid state. It gives you do calculations, it gives you critical value of lambda. Again, this cartoonish paper, actual behavior, it's a little bit more involved, but then we'll need to talk about details. And this gives you phase diagram of which at this moment, I'm just showing you this line. This is where, coming from Fermi liquid state, you start seeing the appearance of bound state. But then it turns out that if density is 0, that was the whole story, 2.5. If density is finite, we find out by explicitly, that's simple calculations. You calculate energies, and it turns out there is a range of real phase separation in the sense that you ask which state has the lowest energy. And it turns out that the lowest energy is Polaron with some density N1 and Fermi liquid with the remaining density. And then N1 varies between 0 and 1 end and total N. Sorry, this is when N1 is N, this when N1 is 0. So this full Fermi liquid, this full Polaron state, and the state which is in between. Yeah, so we have this phase diagram. And again, to get evolution requires efforts. To get this is just energy consideration. And very final aspect, yes, we need to combine this with this wonderful picture that Migdal-Eliashberg theory has its own cutoff, this line. So now let me take with plus sign that one and this one. And this is my last slide before conclusions. So basically we get what I told you before, Polaron gas, we get Fermi liquid, we get separated phase separation region. And along this line, the system first forms charge density wave before Polaron form. And then Polaron forms already out of charge density wave state. We put it as dashed line. Probably phase diagram is more complex here. But all we want to say is this is a metal. This is insulator. This guy has a true gap. This is pretty much what I want to tell you. But maybe the last point I want to say, since again, this is a collaboration on superconductivity, and electron phonon superconductivity is part of the story. Here, once we switch from spinless to spinel fermions, this is a bipolar on superconductivity. There is a region here where, before Polaron forms, Fermi liquid wants to go into charge density wave. Near this point, this is my beginning. I want to make a full circle. Close to this point, you get a story about superconductivity mediated by by soft charge fluctuations. If you find a pairing channel for this, you need a proper lattice, etc. But if you find a proper channel, you find out that there is superconductivity here. But it by no means given by Allen-Dynes formula. Allen-Dynes says for special case when phonon frequency vanishes for all Q simultaneously. It's a little bit pathological case in this regard. So what happens here? It's vanishing, but only at one frequency. You need fluctuations around this frequency, integrate over these fluctuations, you get a totally different behavior. And I guess that's all I want to say. So basically what we said that for fermions interaction with Einstein phonon, this Polaron formation is completely decoupled from the point of internal instability of Migdal-Eliashberg theory, that Polaron states come from high energy fermions. And I guess this is from theory perspective, this is the main message. And this we clearly see by looking into how to reproduce exact solution, where this exact solution come from. And finally, again, at small density Polarons form a Fermi liquid states. Form via Fermi liquid states is internally stable. If we go to higher densities, then situation is more difficult. But thank you very much.
Okay, thank you for finishing right on time.
Almost.
Exactly. We have many questions. Steve, Tero, and then Jon.
See, I'm not going to get criticized by.
Can you please use your
I was terrified. I don't. Can you go back to your last phase diagram?
Which I understand is cartoonish.
Yeah. So, I don't understand the Polaron gas. I would have thought that phase separation eats most of that region. I mean, suppose we go to lambda.
Most likely, you're right. And this is the region of phase separation.
Yeah.
However, this is beyond what we can do.
Okay, but you can go to large lambda. In the large lambda limit, then you get classical Ising model with interactions that are of order 1 over lambda between classical bipolarons. And
this would require us to, when I said it's not a model, it's what we can do or we cannot do.
Okay.
So far, we didn't go beyond this story that let's look at the density of states. There is a continuum, there are peaks, and continuum eats up peaks.
Okay.
We didn't ask a question what goes into how this arrangements of
Yeah.
polarons is affected by the presence of this continuum nearby.
Okay. Anyway, the point is that in the bipolaron limit or polaron limit, the as you said, the renormalized hopping is exponentially small.
Yes, yes.
So you can ignore the hopping. It's just classical particles interacting by interactions that can be computed in powers of 1 over lambda.
Yeah.
Repulsive interaction.
Repulsive, yeah.
So it wouldn't lead for.
Yeah. Well,
No, it'll lead to a series of
It
charge
may.
density waves
It
with
may
like
lead to
commensurate
series
charge
of
density
waves that
waves.
gives rise to phase separation. Again,
Yeah.
please, this is where we're standing.
Okay.
We're happy with what we get. Next one will be next level of this
Okay.
consideration.
Thanks for the excellent talk. You mentioned in the beginning of your Migdal-Eliashberg story that you have actually 3 parameters. So, but you didn't really touch. I mean, the third parameter, this alpha, was always small.
Yes.
So, what was the difference? I mean, you say that it's a ratio between omega 0 and Fermi energy,
Yes.
whereas elsewhere you talked about bandwidth. So
No,
what is
but what
that?
I said is that even if I take, what I said is this, for density, generic density, Fermi energy and bandwidth are comparable, right? So basically it's the same condition. For density very small, we have to be a bit accurate. Because as you know, in the limit technique and the limit when density goes to 0, there is no Migdal theorem, because again, AF goes to 0, and if you do calculations, you find that instead of small parameter, you get parameter of order of 1. So there is a story. We don't want to be there. So we want to take, even if I take about small n, it's always assumed that this parameter is already small. It's not a big deal. We can do calculations, and we see numerically clearly that we don't see any indication that there is some diving or something. It's just lines that keep going to 0 frequency without any appreciable changes. But to be accurate with theory, this is what we do.
Yes, I have one question. Maybe if I misunderstood, but you said that when you enter into the charge density wave limit, your Migdal-Eliashberg theory breaks down, kind of. But I don't really get that point, because if you go to the charge density wave, you will have like a new crystal structure, and you could effectively also apply Migdal-Eliashberg theory for that new structure, right?
Well. In some sense, I agree with you, but let's put the words accurately. Migdal-Eliashberg theory is a theory of a normal state of a metal, and so the only instabilities that they consider, Eliashberg consider was superconductivity. It's just a matter of semantics.
Okay.
Now, what you are asking is a more interesting question. When the system becomes charge density wave order, of course, I need to reconstruct excitations. Right. Not too many people actually discussed accurately perturbation theory and role, for example, or vortex correction in a situation when you reconstruct excitations, right? And suppose that this is some incommensurate charge density wave. Then you have Goldstone modes. You have the sliding mode, right? So how it affects the behavior. We know some of the answers for spin case, but spin case is different because then you don't have analog of Debye frequency, or you don't have analog of Debye of sound velocity, right? Or, you know what I mean, that all velocities are Fermi velocity for the case of electrons. So all I'm trying to say very quickly is that you're most likely right, and there is another Migdal-Eliashberg theory on the other side, but it would be good if somebody will check it. And you see, in our case, yes, there is a range where this works. But in other ranges, before we go into charge density wave instability, something else happened. And something else are bound states.
Thank you.
Can I get back to, you had a slide where Fermi liquid eats polarons. So it was before this one.
This one?
No, earlier, just with density of states or whatever, with bands. Yeah, here, yeah, this one. Yeah, so I just wanted to understand some simple things. So if I mean, in the simplest case, with strong electron-phonon interaction, basically it's a single-site problem. You mentioned Holstein polaron, and the peaks are basically electron excitation plus a number of phonons.
Right.
Okay, so 1, 2, and so on.
Right.
And the the bandwidth, this narrow bandwidth at the smallest energy corresponds basically to orthogonality catastrophe, because you have to shift your phonons between empty and filled state by a lot. Okay, and that's just Anderson's orthogonality.
No, it's Holstein's orthogonality.
Holstein. Okay, sorry. Yes, yeah, that's true. Yes, yeah. Yes, yeah, and then when you go to higher energies, basically you need a smaller displacement, and basically that gets
you
you
put it this way,
right.
yeah.
Yeah, this is a simple way to put it, and the usual way, I would say. So the thing that I'm trying to understand is that basically this picture means that you have gaps in the spectrum. So if you try to tunnel an electron, there will be gaps between, yes, yeah, and then they eventually vanish. And I'm just wondering whether it's a true gap or it's
Yeah, or pseudo.
or yeah, whatever you call it. Yeah.
Okay, again, don't over-exaggerate what we did. We looked into this range. We looked into this range. We said it looks like continuum. We know that there is exponentially small widths of the state. Next stage, whether there is any tunneling. Probably it is. Probably it is. So I don't think that there will be a really true gap. But still, there will be peaks, sharp peaks in the density of states.
Of course, because it's just, it's replicas of a...
Right.
Phonon
So
replicas of
then
a
all I
state,
need, sharp peaks in the density of states and big continuum approaches.
Okay,
and
so it's basically
eliminates
it's
this.
too cold of a picture.
Whether it's true gap here or some small, most likely, of course, as you said, there will be some tunneling.
All right, okay, yeah, thanks.
Your phase diagram, going back to the answer you gave a moment ago about CDWs, you said, look, if it's incommensurate, you can have Goldstone modes. That's Froelich mechanism of superconductivity. It doesn't work. You have pinning. Can't you just ignore this? That seems to be sort of a false objection. Just say, yeah, it's incommensurate, but these won't play a role.
I guess the question was different. The question is, can we still have a theory in which vertex corrections are small here, and we create theory that vertex corrections are small here? Then you can ask a question about superconductivity in this theory.
No, but your answer was, if you have incommensurate, you'll have Goldstone modes, and they will cause a problem. It sounded like that was...
Cause a problem for vertex corrections.
Right, but do you even have to consider that? Because there's always some pinning. And can't you take this sort of experimental fact and get rid of that and progress?
If I have a Hamiltonian, sorry, I have to deal with it.
Okay. All right.
So in this phase diagram, your CDW here is that's a metallic CDW,
Here is metallic.
and then the dashed line.
That line, yes.
And-
Again,
and-
we are in the range where we can only
Yeah.
draw lines
Okay,
approximately.
got it.
Yeah.
One question? So I have a question.
Yes.
This is also related to something that we've been working on with John Sos and Jonah. But basically, let's imagine a system where you have your flat band. So but there can be two, even, right, your band is one-yearizable because single site model in that limit. But even in that limit, there can be two types of one-yearizable flat bands. There can be, like, for example, sp hybridization, just in one dimension, where the Vanier center is moved in the middle, or where the Vanier center sits on the atom. Those are two types of insulators. Each of them with a phonon is exactly solvable, but their polaron gases are very different. Just like there's a transition between them. So have you looked at this situation?
We didn't, but well, we're more than happy to look into this.
So the only difference is that in one case, the electron-phonon coupling G of K Q does not depend on either K or Q, which is this case.
Right.
Whereas in the other case, it depends on K, but never on Q. So you can still complete the square and find the exact solution, etc. And the dependence on K is basically the quantum geometry of the covalent bonding. So I would expect,
Wonderful.
I would expect this phase diagram to go.
It's doable. I hope it's doable.
And then we
Same method.
I see, and because we don't know how to add kinetic energy to that, but you seem to have a very good idea how to do it. So you haven't looked at.
We don't look. No, we looked only in this case.
Okay.
Yeah.
Thank you.
Well, the phase diagram was discussed yesterday. So it's really work in progress at the very end.
more questions? Well, then we're basically excellent on time. Let's thank Andrey again.